Hey, this is Mr. Kelly. We're back at lesson 2. This should be fantastic. Hey, I want you to remember lesson 1, how quick that was and how easy that was. That was pretty easy, right? All right, you just keep that in mind. We're looking at page 495. We're in lesson 2. I want to start with the review problems down here. We're going to look at numbers 1 and 2. We're going to start with 1 and 2. So pause the video and complete review questions 1 and 2. Go. Okay, time to see how you did. We have to get x all by itself. That's what it's asking you to do. Solve for x. So, first step here, this is a regular old equation. I'm going to add 1 to each side of this equation. Draw that big old line. What do we get? Y plus 1 equals x squared. Now, to undo the x squared, remember we want to do inverse operations. The opposite of squaring is a square root. But we have to be careful. When we take the square root of a squared and we're solving an equation, we have to include both the plus and the minus, the positive and the negative of that square root. And let me explain why. Way back, I should have explained this before. Way back when we had x squared equals, way back then, my grandma used to, no, way back here, we had a sum term squared and it equaled y plus 1. But we didn't know whether that term was positive or negative, right? So it could have been negative, and when you square it, it turns positive, and it equals this quantity here, which is hard to think about because it's y plus 1. But just know that we had something squared, so we didn't know what it used to be. It could have been positive, it could have been negative. It ended up as y plus 1 because both of them will give you a positive, what do you got? When you square both of those, you get a positive result, right? Okay, yeah. All right, let's look at number 2 then. Same idea. We got to get rid of the 1/4 if we're going to get x by itself. So I would multiply both sides by 4. Let's put a 4 here and a 4 there. That 4 would cancel the 1/4. We get 4y would equal x squared. And at this point, we're going to take a square root. And again, something squared is 4y. I don't know if that was positive or negative, so we have to put the plus minus. So the plus minus 4y, that is what x will equal. And you know what some people might do? They might take that 4 out. Yeah, can we do that? And we'll just call it plus and minus 2 square root of y. But I'm not going to worry too much about bringing that 2 out if that is a little crazy for you. Today's lesson, man, we are going to do some crazy stuff. We're going to look at the root of the matter. This is page 496. Last lesson we talked about inverses, right? So the inverse is when you switch x and y. So we know the inverse of a power function is defined by the set of all points x, y, or x, f of x, which is the same as y, right? I mean, we interchange those. And the inverse will be the set of all points yx, or f of x, x. It's just switching these, right? That's what the mastery check for lesson 1 was on, just switching x and y. So in order to come up with an equation, okay, if we want to write the equation of the inverse, then we're going to do something very similar. We're going to switch x and y, but then we have to solve for y and get y all by itself because, as you know, we graph y based on x, which is the input. So here is the example that is in your book, f of x equals x squared, or y equals x squared. If we want to find, I'm just going to work it out, even though it's the same. If we want to find the inverse, we take the function and then we switch x and y. So it becomes x equals y squared. But now we have to solve for y. And this is where those plus minus things came in. When we take a square root of both sides, when you take the square root of a squared, we have to include a plus minus on the other side. And so when we solve it for y equals plus or minus square root of x. The inverse of f of x equals x squared is y equals plus or minus x. Wow. So the first question here is, why must you write that plus minus? And we just kind of talked about it. But for each value of x that's greater than 0, there's both a positive and negative value of y for the inverse. And I'm going to make this real quick, but last lesson we talked about graphing those inverses, right? So what if I were to graph y equals x squared? What does that look like? Well, we all know that that is a u. That's a pretty good graph for me. So what if we were to graph the inverse? Remember, we have this piece, which would be the positive square root of x, and then this piece, which is the negative. We have a positive and a negative. We need plus and minus. Notice the worked example does not write inverse notation, though. It doesn't use that f of -1 of x. Why not? And if you remember from the last lesson, it has to be a function. The inverse has to be a function And check out the red curve over here. That's not a function. That fails a vertical line test. So you can only use inverse notation when the inverse is a function. Easy peasy. Let's move to page 497. We're going to look at the square root function in a little more detail here with a graph and a table. So let's use the ordered pairs in the table and what you know about inverses to graph the function and the inverse. I kind of did like a rough sketch on the page before, but I want you to actually graph it this time on the graph. So use this table. This is the function f of x equals x squared, and then also graph the inverse on this graph. Pause the video and get her done. Okay, here's what I did. This is what I did. I plotted these points over here, and that is f of x equals x squared. By the way, always a great idea to label what you graphed so people know which graph is which. And so this is f of x equals x squared, so I label it, and then I just plotted all these points, right? And then we learned in the last lesson that the inverse is just switching the points. Now, maybe you didn't want to do that, so you can just use the equation that we came up with just to verify that that is the inverse. So if x equals 9, like it does here, I should get a negative 3. But our equation says plus or minus square root of 9, which is 3, so we get plus or minus 3. So if you notice, if we input a 9, working backwards, we get that negative 3, but we also, down here at the bottom of the table, get that positive 3. So there's the plus and the minus 3. And for 4, we have plus and minus 2, so on and so forth. It gives me these points when I plot them. But again, you already know how to do this. We did this last lesson. So we're going to draw the nice curve here and then answer the wonderful questions. That is fantastic. Now, normally I put a little y equals x in there. And that brings us to our next question. What point or points do the two graphs have in common? Well, if you notice, they intersect right here. That's 1 point. So 0, 0. Let's write that down. So 0, 0 and 1, 1. And why is that? Well, both are on that line of reflection. Let me bring that back. Here is that line of reflection right here. Y equals x. And check that out. 0, 0 and 1, 1. Both fall on that line of reflection. So when it gets reflected, it just stays put because it's on the line. It doesn't move anywhere. Furthermore, if we look at the table, that's the point 1, 1 and 0, 0. X and y are the same. Check it out. X, y. X, y, they're the same. So if you switch them, guess what? No change. Fantastic. Now let's go down to number 2. We're going to describe the key characteristics of each graph. Go ahead and fill out, pause the video, and complete number 2. You should know this. Figure out the domain, the range, the x and the y intercepts. Pause the video and go. Now here's what I did. I brought that graph down so I could look at it. Let's look at the domain. All right, so the domain are all the x values. I'm going to scan this x-axis here. I kind of look at it like a vertical line going through. The domain, that should be negative infinity to positive infinity. All right, if you can't remember the reasons why for that, then please ask your teacher. The range, it doesn't start until 0 and it goes up to infinity. All right. The x-intercepts, well, that's 0, 0. I'll just write it as a point. And the y-intercept, guess what? 0, 0. Now, when we look at the blue graph, which is the inverse, it's a little bit tricky. The domain starts here at 0 and it goes to infinity. So hopefully you had 0 to infinity. The range, though, it's going to go up forever. It's going to go down forever. So that is negative infinity to positive infinity. The x-intercept still 0, 0, and the y-intercept likewise, also 0, 0. So did you notice this? There's a little pattern. When you look at the inverse, remember what we did? We switched x and y. And x, that's the domain, and y is the range. So when you switch, guess what? This domain becomes that range, and this range becomes that domain. How crazy is that? Same thing for the x and the y-intercepts, even though I can't really tell this because they're both the same. But what you get for the domain of the function should be the range of the inverse, and vice versa. Fantastic. So now moving on to page 504, where we look at the cube root function that comes from y equals x cubed. All right, let's look at this. Y equals x cubed. That's the function we're dealing with here, right? There it is. Okay. Now I want to find the inverse of that, so we switch x and y. All right, so x equals y cubed. How do we get rid of a third power, a cube? We can take the cube root. Now, do we need a plus or minus here? And the answer is No, we do not need a plus or minus. You know why? Why is that? I don't know. That's going to be one of our questions, isn't it? We will answer that on the next page when we get to it. But right now, what I want you to do is to graph the function y equals x cubed and its inverse, just like we did for the other function y equals x squared. So graph the function and the inverse on this graph. Ready, set, go. Okay, let's check your work. Does it look like mine? Here's what I got. I graphed the original function and I labeled it c of x because that's what they called it. And then I switched all the x and y's and I graphed the inverse, which I then called c negative 1 of x, or the inverse of c of x. Okay, so that's pretty easy. Just graph the points and then switch, graph -8, -2, that would be down here for the blue function. And then explain how you determined the coordinates. Well, let's do that. Let's explain. And again, you can pause the video if you need more time, but I basically switched the x and y values to get the coordinates for the points of the inverse function. And then the next question, part C down here, says, what points do they have in common? It's the same as the x squared, right? They have, except this has a -1, -1, and we have a 0 and a 1, 1 in common, because those points have the same x and y coordinates. So when you switch them, guess what? You get the same point. Easy enough. So moving to page 505, why does the inverse of the function not have a plus or minus? I promised we'd get back to this, and here we are. We're back at it. So I'm going to let you look at these two different functions. We're going to look at just y equals x squared, and then y equals, what do you hear? Y equals x cubed. And we're going to find the difference between the two when we're looking at them. Okay, so y equals x squared. Let's plug in some points here. Let's plug in a -2. So what's -2 squared? That would give us a 4. Let's plug in a -1. That would give us a +1. Let's plug in a +1. That would also give us a +1, right? So I'm plugging it in here. I'm squaring the numbers. Let's do 2 and call it a day. 2 would give us a 4. All right, so when I look at the inverse, well, let's not do that. Let's go to this one first. Let's do the same thing. So if I plug in a -2, so -2 to the third power is -2 times -2 times -2. That's -8, right? And then -1 to the third power is -1. +1 to the third power is +1. And then 2 to the third power is 8. Okay, so now let's look at the inverses. When we found the inverse of y equals x squared, what was that? We found y equals, and we said, what? The square root of x, right? So that's working backwards. So if I want to go from this number to that number, I just take the square root. So what is the square root of 4? It's 2. However, remember that two numbers, when you square them, will end up to be +4, both -2 and 2. And we don't know if we're working backwards which one we have. So that's why we need the plus or minus. Let's go over here to y equals x cubed. If I take the cube root, so that would be this, y equals the cube root of x. Okay, well, let's work backwards. What if I plug a -x or a -8 into the x? Is that possible? The cube root of -8. Or is that imaginary? And guess what? That's not imaginary. That's a real number. There's only one number that when you multiply it times itself 3 times will give you a -8. The cube root of -8 is actually -2. And it's the only possibility, which is not the same as over here when we square things and they turn positive, and we didn't know. So there's only one answer for this. This ends up being a function. We don't need the plus or minus because y equals the cube root of x is a function. It only has one y value for each x value. Let's actually write that out. The inverse of c of x is a function. For each x, there's only one value of y. That's why the plus or minus is needed. And then why don't we have to restrict the domain to write the inverse with a notation? Okay, look at the domain here. We don't have to cut any of that off to write. This is a function. So because the inverse is a function, we can use inverse notation. If you remember, that's called invertible. That came from lesson 1. So this function is invertible, which means the inverse is a function. Very cool. So let's look at number 4. I put the little picture of our function and its inverse right here, so we kind of help us along a little bit. But this will be a little bit boring. So c of x equals x cubed. Let's write the domain of that. So what's the domain? Well, it's going to go left forever. It's also going to go right forever. So the domain is going to be -∞ to infinity, And remember what we learned before? So the inverse will have the same range as the domain of the function. This is a little bit cheating, but they end up being the same, right? Because the x here is the x here is the y there. And then the y here, the range, is also negative infinity to infinity. That's why I said it was a little bit boring. But that ends up being the domain of the inverse. Negative infinity to infinity. Come on, infinity. The x-intercepts, well, where does it cross? Just 0, 0. And it only crosses the y at 0, 0, which means the x-intercept here is the y-intercept here, and vice versa. Easy peasy. Does the inverse function have an asymptote? Does this have an asymptote that it never crosses, that it, we're talking about the inverse function is the blue one. Is there like a horizontal line that it never crosses? The answer here is no. Like this will go up as high as, you just have to go far enough to the right, and this function will keep going up higher and higher eventually. Even though it might look like it has an asymptote, it really doesn't. It'll keep going up forever. So that is our answer to 5. As x increases, the cube root of x increases towards positive infinity, and as x decreases, as x goes to negative infinity, the cube root also decreases towards negative infinity. So now we're going to look at some the inverses that have some science applications. These square root and the cube root function, they're called radical functions. So if you hear about a radical function, it just means you have a cube root, a square root, something like that. It involves a radical. That's why they gave it the name. And they get used all the time. So let's look at a couple. So now looking at page 508, we're going to look at an application of these radical functions. The time it takes for one complete swing of a pendulum depends on the length of the pendulum and the acceleration due to gravity. If you guys have one of those cuckoo clocks in your house, you can tell this because the weight at the end, there's the weight, the thing that swings back and forth, the pendulum, you can change the weight of it, right? So, I mean, really what you're doing is changing the length of it because that's where all the weight is. And so the longer it is, the longer it takes to go back and forth. That's how you adjust those clocks, by the way. They go faster if you move that little weight up. But the formula for the time it takes a pendulum to complete one swing is, and here we have t equals 2 pi square root of Lg. T is the time, L is the length of the pendulum, and G is the acceleration due to gravity, which I know you guys in physics already know that acceleration due to gravity is 9.8 meters per second squared. All right. Write a function t of L that represents the time of one pendulum swing. Really, all they want here is to look at that G, acceleration due to gravity. We can plug in that 9.8 right to the G. That's what they want us to do. And then we come up with this equation here, 2 pi times the square root of L over 9.8. And we notice there's a square root involved, so this is a radical equation. Now they want us to use technology to sketch a graph. So let me show you how to do that. This is our handy calculator. I cleared the RAM, if you remember how to do that. I'm going to go to y equals, and I'm going to type this in. 2, there's a pi here to the right, so I'm going to hit second pi. It's going to make it really, really accurate for us, right? 3.14159, all that stuff. Then we're going to take a square root of L. Now we're going to have to use x in the calculator, which is right here. And then we'll divide it by 9.8. I'm going to make sure that's still underneath the radical, which it is. It appears as though we're good to go. I'm going to look at the graph right here, and we get a nice radical function graph. But they want us to graph it here. So if I were doing this, which I am right now, so I'm just going to go to the table. And I'm going to plot some of these points the best I can on the graph. You're going to have to estimate because these are all ugly numbers. There's a pi involved. And so after we plot some of these points, you don't need to plot them all, but you plot a couple to get a good feel for the graph, and then you label it T of L, and then we make sure that everything makes sense here. Time, our independent variable is time, and our dependent variable is the length of the pendulum. So does this make sense? Like the longer the pendulum gets, the longer it takes to make one full swing. All right, well, yeah, that kind of makes sense. But this is how you could use your calculator to help you graph a real graph, because you're going to have to do that, right? And if you want to see the values, you can just go up into the table, and you can even scroll down, and see some of these values here. All right, so that is number 2. So let's now describe the characteristics of the function, its domain. So the domain would be what? Well, I got to go back and look at this. What are we dealing with? We're dealing with the domain. What are we plugging in here? We're plugging in L's, the length of the pendulum. So that's our domain. What is our range? The range would be t, okay, which is time. All right, so how am I going to write this? The domain that L had to be greater than or equal to 0, right? Because we're plugging in an L, that is our domain. It's like the X value, it's the input. If we go back to our graph, we look, it's the length of the pendulum, so it has to be here, 0 all the way out to infinity. Theoretically, you could have an infinite, so we could say that L has to be greater than or equal to 0, or if we want to use interval notation, we could say 0 to infinity. That would be fine. The range is the time, right? So the time also has to be greater than or equal to 0. We can use interval notation for that as well. The x and the y-intercepts, let's write those down. X-intercept, y-intercept are both 0, right? So it's 0, 0 for both of these. Voila. Okay, explain your reasoning. Well, it has to be positive because you can't have negative length of pendulums. That don't make sense. You can't have negative time. I mean, in this problem, you can't. It doesn't take negative time to do something. So let's write that. All right, we can write that out. Negative values don't make sense. Therefore, the domain and range must be positive. And number 4, how long does it take for one complete swing? Number 4 says, how long does it take for one complete swing? Oh my goodness. If the pendulum is 0.5 meters. Well, let's just use our little formula here. What was it? T of L, right? So T of L equals 2 pi and the square root of L over 9.8. All right, so I want now the length they're telling us is 0.5. So that's going into the L, and that equals 2 pi times the square root of, the length is 0.5, so I'm going to put a 0.5 in there, all over 9.8. But guess what? We have our calculator. Do you remember how to do this in your calculator? Check this out. I already have, let's see, I already have here's the formula right here. I'm just going to quit. I'm going to hit vars. I'm going to go to the right for y variables, the function. I'm going to pull up y1, and I'm going to plug in a 0.5. And that'll just do it for me, right? 1.41. All right, so I know this all equals 1.41, or you can do it manually, right? 1.419. I like my calculator trick, though. That makes it nice and easy. And lastly, let's go to page 510. I'm going to have you read this scenario and then see if you can answer number 6. I think you can do it. It's not that difficult, but you need to know how many seconds are in the day. You know what I mean? There's my hint. So pause the video and do number 6. Okay, so here's what I'm getting. A focal pendulum, just kind of swings back and forth. And they said a museum has a focal pendulum that's 200 meters long. So really what I want to do is use our formula here, and I plug in a 200. And when I do that, T of 200 equals 28.4 approximately, right? So that means it takes about 28.4. So that's one swing. Well, 28.4 seconds is one swing. How many seconds are in a day? And then I can kind of figure that out. So one day, that's tricky. What do we have? Well, there's 60 seconds in a minute, right? In 1 minute. And there are 60 minutes in one day. Sorry, in 1 hour. And there's 24 hours in one day. Remember doing this in physics? It's fantastic. So what do we get? Minutes will cancel, hours will cancel. We get seconds per day. 60 times 60 times 24. I think that's like 86,400, right? That's how many seconds there are per day. So if one swing takes 28.4 seconds and there are this many seconds in a day, we can take that number of seconds in a day and we'll just divide it by how long it takes one swing, which is 28.4. And this will give us approximately 3,042-ish, I think it's 0.3, swings per day. Hey, how about that? That is our application problem. Woo, this is a long video. I'm ready to take a nap. So good luck. Go ahead and try your problems. Some of them are application. You're going to have to work your way through some of those. Make sure you ask a question with your teacher if you are struggling. Good luck to you all out there. This is Mr. Kelly in K-Town. Remember, it's nice to be important, but it's more important to be nice. See you.